I want to call Murakami Sensei for a welcome address. Thank you.
Okay, thank you, Paolo-san. I'm Masato Murakami, President of Shibaura Institute of Technology. On behalf of SIT, I'd like to extend my sincere welcome to distinguished speakers and participants to Italy-Japan virtual workshop on materials for high-efficiency renewable energy systems. This workshop was first planned to be held at our Shibaura campus on the Italian Research Day. Due to the outbreak of COVID-19, Dr. Paolo Mele, professor of SIT and the chairman of the workshop, kindly arranged online workshop. Thank you, Paolo-san, for your effort. The aim of the workshop is to reconnect Italy and Japan in the science and technology field as part of the Italy is Back to Japan program of the Embassy of Italy in Tokyo. The topic chosen is renewable energy, which is an important tool for fighting against the climate changes and for global sustainability. I learned that Italy is co-organizing the next COP26 with the United Kingdom on climate changes, which will be held in 2021. Today's workshop will focus on the aspect of improving energy efficiency through the material development for renewable energy systems. I hope this virtual workshop will be a fruitful one for everybody. Please enjoy it. And once again, thank you for attending this exciting event. Thank you.
Thank you, Professor Murakami, for the kind words. And now I want to call His Excellency Giorgio Starace, Ambassador of Italy, Japan, to give his foreword. Please.
Thank you. Grazie, arigato gozaimasu.
Arigato gozaimasu.
Dear Professor Murakami, dear speakers, dear participants, it is a great honor and pleasure for me to present my greetings at the opening of the Italy-Japan virtual workshop on materials for highly efficient renewable energy system, co-organized by the Embassy of Italy in Tokyo, together with the Shibuya Institute of Technology. First of all, I would like to thank very much the President, Professor Murakami, for hospitality, Professor Paolo Mele for the organization, Dr. Traversa, Enrico Traversa, the scientific attaché of the embassy, for arranging my presence and the contribution to this workshop. And all of you to be present today. As part, as it was mentioned before, of the Italy is Back to Japan program of our embassy, and of the Italian Research Day in Japan initiative of the Italian Ministry of Foreign Affairs, this workshop is the occasion to reconnect Italy with Japan in the science and technology field, now that the emergency for the COVID-19 pandemic is less stringent, through in a virtual, not a physical way, unfortunately. The emergency of lockdown has suspended many of our activities, including research. But now that the pandemic is under control in Italy and in Japan, after the efficient action of both the Italian and Japanese authorities, in Italy and in Japan, the discipline that was shown by both our people, what is concerning Italy, we are very confident that by July, the last COVID patients will leave the Italian hospitals. COVID, we really much think that the topic that is chosen for the workshop, in agreement with the Shibaura Institute of Technology, is renewable energy, which is, on our opinion, a very important tool for fighting climate changes and for sustainability. The European Union has launched recently the EU Green Deal, and a green recovery package was implemented to cope with the economic crisis after the pandemic, seeing this as an opportunity for fostering green policy. Italy is proud to be, since long, on the forefront of this global challenge. A champion in green energies, my country generates 33.9% of its energy production through green energies, ranking among the best performers in Europe, second in terms of production, and third in terms of consumption. Moreover, the International Energy Efficiency Scorecard ranked Italy as the world best performer in terms of energy efficiency. We are therefore extremely pleased that also in Japan, the Ministry of Environment, Shinjihiro Koizumi, is calling for international collaboration for green recovery, including society decarbonization and circular economy. Moreover, Italy is co-organizing with the UK the next COP26 on climate changes, which was postponed to 2021, and our intention is to strongly engage Japan for ambitious outputs of the conference. Therefore, talking with Japan about renewable energy is very important to stimulate new collaborations. In particular, this workshop will focus on the aspects of improving energy efficiency through the materials development for renewable energy systems. We are going to listen for 4 distinguished speakers, 2 from Japan and 2 from Italy, all world leaders in their fields. I am sure that you will enjoy the event, and I wish all of you a very fruitful discussion and a very stimulating exchanges of ideas. Thank you very, very much for your attention.
Thank you, Mr. Ambassador, for your forward and inspiring words. So I want to pass to the first talk of this workshop by Professor Masato Murakami, the president of Shibaura Institute of Technology. So, Professor Murakami, please.
Okay, can you hear me?
Yes.
Okay. Well, today I'd like to talk on with the title, Can Superconductivity Save the Earth? Well, as you know, superconducting materials are very attractive for various engineering applications since they exhibit zero resistivity. But until 1986, the critical temperature of superconductors stayed very low. So we need to use very expensive liquid helium to cool the superconductors or for engineering applications. So many people, searched for higher TC materials. In 1986, TC above 30K was observed, and which had boosted the superconductivity fever. And soon after the discovery, YBC, or that's yttrium barium 2 copper 307 system with TC 92K, that is higher than the boiling point of liquid nitrogen, was discovered. And right now, practical applications of oxide superconductors or high temperature superconductors are mainly based on yttrium barium copper oxide or bismuth strontium calcium copper oxide. Well, this is a crystal structure of yttrium 12307. I will not go in detail, but here I would like to say that the yttrium site can be replaced by many other rare elements. And here is the crystal structure and critical temperature of rare earths 1 to 3. Like yttrium, lanthanum, neodymium, samarium, europium, gadolinium, those forms 1, 2, 3 similar structure. And it's interesting, some of them shows even higher TC than that of yttrium system. And the melting point of these materials are also different, which lead to the possibilities, various processing routes to make superconductors. This is one of the demonstration. This is called top-seeded melt growth processed yttrium barium copper oxide. You can see permanent magnet is levitated over TSMG YBCO cooled by liquid nitrogen. And we have succeeded in levitating a lady or human levitation many years ago. And our demonstrated attracted the attentions of many public people. And I'm very happy I was levitated with Miss Hokkaido or Miss Gifu. And we also levitated a small wrestler. This is the photo. Can you see him? The young emperor, now Majesty Emeritus, received the explanation of superconductivity from myself. He was young and I was young. And I invited the emperor to be levitated by the superconductor. And he said yes. Whoa, I said, I'm very lucky. Then imperial police rushed in and stopped it. Too dangerous for the emperor. So instead of the emperor, I'm standing on the levitated disc looking down at the emperor. Well, then why I did the human levitation? In those days, IBM, Bell, Hubble researchers claimed that high temperature superconductors are not usable because there's no persistent current. And I claim it's not true. Then how I could prove it? That was a human levitation. Professor Tinkham at Harvard University told me, I believe you if you can levitate a person. So I did. Let me tell you the mechanism behind this. There are two types of superconductor. We got type 1 and type 2. Type 1 superconductor is not usable because the critical field is too low. The superconductivity is broken at very low field. And most practical superconductors belong to type 2. In this type 2 superconductors, in the medium field, superconductor allows the penetration of external magnetic field. With this mixing state, the superconductivity can survive up to very, very high field, like 100 Tesla. That means engineering application is possible. But there was another problem. That is, if we pass current in the mixed state, Lorentz force act on the flux side, or magnetic field, quantized magnetic field, or vortex. And lots of normal conducting electrons are there. So if the flux side moves, then resistivity appears. And we call it flux flow resistivity. So in the case of type 2 superconductor in the mixed state, we cannot achieve zero resistivity because of flux law. So we have to stop flux law motion to realize zero resistivity. How we can do it? It's very simple. Microstructure control. Here is a schematic illustration. Pure superconductor, there is no zero resistivity current, zero critical current. But if we introduce non-superconducting particles into the superconducting matrix, fluxoids are pinned by those particles. We call it pinning center. Then, as long as pinning center stops the motion of fluxoid, we can achieve some amount of critical current. And depends on the microstructure, we can achieve very large critical current. That is key. And in the case of yttrium-123, there is a yttrium-211 non-superconducting particle. Here is a TM microstructure showing that very small 211 particles are embedded in yttrium-123 matrix. So we need to control microstructure such that non-superconducting particles or pinning centers are finally dispersed in the superconducting matrix. And lots of pinning centers are known in conventional superconductors, like a titanium precipitate in niobium ti, or grain boundaries in niobium-310, or 211 in yttrium-123. Then the second one. Let me introduce electromagnetic induction, very simple one, everybody knows it. When we approach a permanent magnet toward the conductor, currents are induced to give a repulsive force. But when we try to move a permanent magnet away from the conductor, then attractive force will be gained. This is called the Lenz's law. And induced current flows in such direction that it opposes the change producing it. So in the case of a superconductor, if we approach a permanent magnet toward the superconductor, induce a current. And since there is no resistivity, supercurrents will flow persistent. So permanent magnet is floating forever as long as we cool them by liquid nitrogen. So human levitation, as long as we cool the superconductors, then human levitation continues without any decay. This clearly shows that supercurrents are non-dissipative even in high temperature superconductor. So I claim that supercurrents are persistent in oxide superconductors. If you remember electromagnetic induction, it shows currents are flowing in bulk superconductor. That means bulk superconductor can become a kind of quasi-permanent magnet. And how large fields they can trap? Well, at 29 K, they could trap 17 Tesla. That used to be the world record. And our paper appeared in Nature in 2003. You know the story of Moses? Moses parted the Red Sea by the power of God. But Musato parted water by the power of superconductivity, because water is a diamagnetic material and they repulse magnetic field. But you cannot see it with a very small magnetic field. But if you have a very, very strong permanent, you can demonstrate this. Then what can we use this strong magnet? Well, there are many, many applications. One is medical treatment to recover cartilage without surgery. You know, cartilage is a soft bone-like structure covering the knee. And once people damage it, it's really difficult to recover it or regeneration. But if we inject medicine, liquid medicine containing stem cells, it's easily to recover. But we need to add ion particles. And the idea is we apply field with our strong magnet, then injected medicine is attracted to the diseased part. And here it's important, iron is a human-friendly material. And I did this experiment using pig. We damaged the cartilage, and we treated this kind of injection. Then we found that in 3 months, this cartilage recovered completely. And this is the schematic illustration of medical treatment for future regeneration of knee cartilage with our technique. Now, next topic, the superconductivity saved the Earth. Here, I'd like to talk about power transmission and magnetic shield. Well, I talked about superconductor, but of course, you know, superconducting wires attractive for various applications. And already people made oxide superconducting wires. One method is we insert raw powders of high temperature superconductor into metal tube and just draw it. It's called the powder in tube method. The other technique is called the coated conductors. It's based on thin film technology. On a metal tape, we coat superconductor using like a physical vapor deposition or chemical vapor deposition. And already many teams in the world have succeeded in making long-length superconducting cables, which was installed in superconducting cable pipelines and tested by many companies like TEPCO, Tokyo Electric Corporation. And recently, a team in Chubu University succeeded in making 500-meter test superconducting cable lines in Hokkaido. As you know, the solar power is the source of energy for all creatures on Earth. However, the sun is quite a dangerous star because it emits solar winds with radioactive plasma. If we cannot seal it, all terrestrial creatures will die. Then why can we survive on the Earth? It's because of the Earth's magnetic field. Geomagnetism protects us from the solar wind. Have you ever heard about the Van Allen radiation belt? The solar wind is shielded by Earth's magnetic field, so we can survive on the Earth. But people know that there is a magnetic field reversible. Earth's magnetic field reversed 9 times in the last 3.6 million years. As long as field is there, it's okay. But during pole reverse, magnetic field disappears. Without this magnetic field, solar wind directly attacks the Earth, and we die. Recently, people found that Earth's magnetic field is decreasing and may disappear in 780 years. What should we do? Well, install superconducting cables around the equator to produce Earth's magnetic field. So, it shows superconductivity can save the Earth. Well, not only the threat of solar wind, there was another dangerous event. That's a solar storm. In 1859, telephone company in Boston detected excessive overcurrent. This is because of the solar storm. And there is data that massive solar storm hit the Earth in 1770. And last year, an ancient document was discovered which shows aurora was observed in Kyoto in Edo period. Massive solar storms, the kind of solar wind, is very dangerous because if it hit Earth, it may cause worldwide damage to modern power grids and electric devices, including computers and AI. And I say only superconducting materials can shield magnetic field. Another interesting aspect of superconductivity is the power transmission. Japanese government proposal, the construction of a solar generation plant in Sahara Desert and deliver electricity to the world through superconducting cable. So if we cover 1/4 of Sahara Desert, we can deliver electricity needed for the whole world. So can superconductivity save the Earth? My answer is yes, it can. However, international collaboration like Italy-Japan friendship is important. Thank you very much for your attention.
Thank you, Professor Murakami, for inspiring talk. So, as I told you, it's no time now for questions, but you can write your questions in the chat. So, it's time to pass to the second talk. From Professor Elisabetta Di Bartolomeo, University of Roma Tor Vergata. So, Elisabetta, please. Thank you.
Can you hear me?
Yes.
Yes.
Okay. Is the presentation on?
Yes.
Okay, so let's start. Okay, good morning, everybody. The title of my talk is Innovative Anodes for Solid Oxide Fuel Cells, Insights on Redoxability and Electrocatalytic Activity. I thank you, the organizer, for the invitation. So, as you can see from the picture shows how limited space is necessary when a photovoltaic efficiency of 10% is assumed. So, apart from solar irradiation, we have also wind and water energy. Thus, it is clear that we will have to rely on solar irradiation as our main sustainable energy source of the future. Thus, we need a tremendous conversion and storage capacity to compensate for intermittency of these energy sources and to have a continuous, reliable energy supply. Reversible solid oxide fuel cells and electrolysis cells have a great potential as such as converter because can convert electricity into fuels or into other chemicals, and it can convert fuel back into electricity. Moreover, reversible solid oxide cells are highly efficient because they operate in the high temperature range between 650 and 850 degrees C. Thus, the solid oxide technology development is on a global agenda. Here, I reported the running funding research project in different areas of the world, as Japan, European Union, and USA. My talk is going to be focused on materials for solid oxide fuel cells. Here is a scanning electron micrograph cross-section of an anode-supported flat cell. As you can see from the bottom, there are in different colors. There is the supporting layer, the micrometric anode, which is a composite made of 40% of nickel and 60% of YZ, yttrium zirconia, the very thin electrolyte, a reaction barrier made of gadolinium doped cereals between the electrolyte and cathode material, which is a perovskite oxide. This is a conventional cell, but the state of the art of materials for FSOFC still presents some unsolved issues. Especially the fuel flexibility and mechanical stability. Specifically, the presence of nickel in the anodic cermet produce mechanical instability due to the continuous reoxidation from nickel to nickel oxide during the redox cycles that brings to anode detachment, and in presence of fuels different from hydrogen, such as methane mixtures or hydrocarbons, nickel produce reduce carbon deposition and coking formation. Moreover, it is easily contaminated by sulfur components. Thus, how to improve and overcome the problems about anodes? To use alternative anode materials, where the metallic nickel is removed or drastically reduced. Many metal oxides had been so far investigated, and here reported a list of the crystal structures. Among those materials, the most promising are the perovskite oxide, even though the main drawbacks is the reduced catalytic activity compared to nickel cermet. So most of the effort of the research activity have been focused on catalyst implementation. To improve the catalytic performance of perovskite oxide as anodic layer, can be used different techniques, such as infiltration, impregnation of perovskite black bonds with different metals, or coating the perovskite anode with metallic salts. In those cases, the limitation is the coarsening of the metallic particles, and the time consuming of those techniques make the scale up impossible. Thus, the exsolution of metallic nanoparticles from the perovskite structure can solve some of those limitations. Catalytic active transition metals are substituted in the B side of perovskite oxide in oxidizing conditions and released on the surface as metal particles once the oxide lattice has been completely reduced. Exsolved particles, here are about 1/3 immersed in the surface of the host lattice and possess enhanced thermal stability and low tendencies to coalesce. Among the most promising perovskite oxide, doped lanthanum ferrites are the most promising. In these compounds, there is a strong correlation between the oxygen vacancies and the B-side oxidation state, as reported in this graph, where we have the oxygen stoichiometry versus different oxygen partial pressure. We see as at high oxygen partial pressure, we do not have almost oxygen vacancies because they are compensated by iron 4+. In the intermediate region, by reduction of iron, the stoichiometry is 1/2 the doping of the A site, and at low PO2, the oxygen stoichiometry still increase up to exsolution of metallic iron in this case, and the oxide substrate collapse. In our group, we investigated several B-side substituted LSF perovskite for different applications. Today, I'm going to show you our last results on manganese substituted oxide compound, starting from the synthesis and focuses on the study of structural evolution, switching between hydrogen and oxygen, oxidizing and reducing condition. Then does investigating structure reversibility, and then promoting an electrocatalyst implementation to design an innovative anode which is redox stable and carbon resistant. Our compounds were synthesized by solution combustion synthesis and calcined at a temperature as high as 850 degrees C. Here there is the XRD diffraction of manganese substituted and manganese-free compound. As we can see, the main peak is shifted toward higher angles, means that the unit cells is decreased due to the lower ionic ionic radius of manganese compared to iron. I want to show you what happened during reduction to manganese-free LSF perovskite, a complete structure instability. As you can see from this XRD, we can observe the iron solution in the pattern, but also the decomposition and the oxide collapsed, reducing in hydrogen at 800 degrees C. The same reduction treatment in LSF manganese perovskite oxide shows a good structural integrity because there is a shift or a transformation between the single perovskite, rhombohedric perovskite of the as-prepared compounds into a Radel-Sepp-Popper structure with iron, exoluted iron, which is the rule of manganese doping. First of all, we investigate the effect on oxygen vacancies, and here it is clear that by increasing temperature, the oxygen released in LSF manganese is much lower than the reference compound. This is true also in reducing condition. In this figure, I reported the TG in hydrogen, and in the same temperature range, also the temperature program reduction measurement, where each peak corresponds to the hydrogen consumed for the reduction of cations. As we can see, again, the overall effect of manganese is to retain lattice oxygen, slowing down the reduction exsolution. Then we investigate the reoxidation again with the TG, and we can see that before and after the reoxidation, a mass gain is really observed, and from XRD pattern we see as iron go back into the structure, because here we have before and after the TG measurement with the reinclusions into the Radel-Sepp-Popper structure, because here in this case the reoxidation is not still complete. Here we have the full redox cycles. As we can see from as-prepared after 10-hour reduction, here there is the enlargement of the main peak, where a single peak is perovskite, double peak is Radel-Sepp-Popper structure. We see that after 10 hours the reduction is complete, but just after 1 hour reduction we can see iron exsolution. Moreover, we have many other peaks that are can be attributed to a metal stable phase, which is manganese oxide that is absent in both as prepared and end of reduction XRD pattern. So which is the rule of this manganese oxide? Is an intermediate compound during the perovskite to Radel-Sepp-Popper transformation that promotes the formation of a single Radel-Sepp-Popper phase, avoiding the structural breakup, as in the case of LSF perovskite. So iron exsolutes like metallic iron, while manganese is in the form of manganese oxide. After reoxidation, we see that after 10-hour reoxidation, we get the same phase with even a sharper peak at a higher angle. So it seems that maybe after reoxidation, we can get a better crystalline phase. So in this way, with this doping, we got a reversible crystal structure. The conductivity properties here, there is the Arrhenius plot of our compound compared to the undoped perovskite. Also in this case, we see that the overall conductivity is decreased, and we observe an activating behavior here and a metallic-like behavior there. The conductivity in LSF is due to the hopping along the chain iron 4 plus, oxygen iron 3 plus, and the substitution of manganese act as a trap for electronic conduction. We also measure the conductivity in hydrogen. As we can see, the conductivity is sensitively decreased, but the value is still acceptable to be used as electronic conduction at the anode side of SOFC. Here is the comparison at the same temperature of the conductivity with the undoped samples. There is more than, there is 1 order of magnitude of difference. So it is redox stable, and it is enough electrical conductive. So what we should do now, we have to think about a catalyst implementation. In our previous work, we investigate as electrocatalyst for dry reforming of methane, nickel-doped, nickel samarium doped seria. So we added 5% of nickel during the synthesis to the samarium doped seria, which is well known to be a good electrocatalyst. This compound, in this compound, nickel behave as a methane activation. Well, then the interaction between nickel and doped seria favors a high tolerance to cooking. So this compound was investigated as a good electrocatalyst for oxidation of cracking products in presence of methane mixture. And okay, so we design our innovative composite anode by mixing the perovskite oxide for the 68%, which shows a better electrical conductivity than nickel or nickel SDC or SDC, with the good electrocatalyst. The overall amount of nickel in our composite anodes is about 2%, which is much lower than the about 50% of the conventional nickel YZ anodes. Here I reported the XRD of the compounds of the anode compared to the single component. What we can see is that in the composite anode we have the presence of iron-nickel alloy. So the iron exoluted from the perovskite and the nickel from the electrocatalyst form an alloy that can mitigate the carbon deposition. We used our anode, our composite anode in a single cells, which is electrolyte supported by using lanthanum, strontium, gallium, manganese as electrolyte, a well-known electrolyte for intermediate temperature application. And we did a pellet, we made a pellet of 400 microns. And then we tested in this temperature range by using, firstly, by using hydrogen. And we got remarkable results, up more than 400 milliwatt per centimeter over centimeter square, with a polarization resistance less than 0.5, which is good for this system. From impedance measurement made at different dilution of hydrogen, we can see that the two semicircles observed from the Nyquist plot measured at OCV are due, so the first semicircle, the low at lower frequency, are due mainly due to the anode, while the higher frequency semicircle is merely related to the cathodic reaction, even though this difference can be further investigated. Then we switched and we tested the same cells in presence of dry methane at 850 degrees C. Firstly, we were interested to check the redox stability in these conditions. So we switched between methane during the day and argon during the night for 1 week. And we could observe, firstly, that the OCV methane is quite good. So it's about 1 volt, which is good. It means that the anode is properly working, and we could not observe any decrease and no self-fooling after one week. We also check the endurance, continuously exposing the cell in dry methane for 14 hours at the same temperature with the same flux, measuring the current density versus time at 0.5 volt. And we see that the current slightly increase, and checking the performance before and after, we can even see that we can get slightly better performance, reaching almost 200 milliwatt over centimeter square. So it means that during the cell is not degrading, and it is even slightly better performances, probably due to the better reduction of the anode side. We check the coking, removing the cells and checking by SEM Raman Spectroscopy. From SEM, we could not detect everywhere on the surface carbon filaments due to the carbon deposition or carbon coking. We can just observe a slightly increase of the grain size of prolonged exposure at high temperature. And from Raman spectroscopy, here we have the GD band, which are typical from the carbon, deposited carbon. We couldn't say that clearly that there is any carbon deposition. Those peaks are related to the iron, they're related to the samples, not to the carbon. So here there is the window for carbon peak. So I can briefly conclude my talk saying that we design a composite anode based on 60% of perovskite and 40% of electrocatalyst. The cells shows remarkably low polarization resistance in hydrogen, good OCV in methane, but most importantly, redoxability and no trace or minimal trace of coking. The rule of the perovskite is the reversibility mainly to the redox cycles and good conductivity in reducing condition, while nickel SDC provides oxygen ions to promote the methane oxidation or the oxidation of the cracking products, while nickel or nickel iron alloy that is formed activate the methane molecules. So I want to thank you for your attention, show you the graphical abstract of our last work, and I would like to thank Materials and Device for Energy Group at University of Rome Tor Vergata, and here in the photo there are the guys involved in this work. I would like to thank you all for your attention.
Thank you, Elisabetta, for your nice talk. So now, please, for any questions, write it in the chat. So now I want to pass the chair to Professor Enrico Traversa for the next part of the workshop. Enrico.
Thank you very much, Paolo. Good morning to everybody in the east side of the world, and good afternoon to all that stay in the east part of the world. It is now my privilege and pleasure to introduce Takao Mori, who's received his PhD in '96 at the University of Tokyo, and now he's MANA Principal Investigator and Group Leader at the National Institute for Material Science in Japan. And so without further ado, I'll give the floor to Takao.
Okay, Thank you very much for a kind introduction. So I will share my screen. Hopefully it works. A little scared. So I hope this screen is visible to everybody. And first I'd like to thank, of course, Professor Enrico Traverser and Professor Paolo Mele for this organization. And also, of course, President Murakami and Excellency Ambassador for hosting this event. So it's a great honor for me to be able to introduce our work on the thermoelectric. And also looking forward to the collaboration with Italian researchers. So title of my talk is Development of Thermoelectric Materials and Modules for IoT Energy Harvesting. So I was already kindly introduced. So we come from NIMS. This is in Tsukuba Science City, not so far away from Tokyo. And I just introduced my group. So there's 7, maybe one of the largest group in the NIMS National Institute. We have 7 senior researchers. And actually, maybe you guess from the pictures, our average age is quite high. I guess it's 52 years old. So I think we also need some new young people too. But 2 new members, Goto-san and Tachibana-san, which joined from April. So we're very happy to have these new, very active members too. And many young people written here. And also a special note to the, we have a good cooperation with Europe already with a French laboratory supported also by CNRS, David. And also I'd like to thank these collaborators from out of the group. And I also like to give this extra side just of the young people here, like the students and the postdocs. So, before getting on, I also like to thank other collaborators from the funding project. So we are very fortunate last winter to get a very large 10-year project from JST called the Mirai project. So Mirai means future in Japan. It's mainly on this thermoelectric material, like standalone power supplies. So, so I also like to thank the ongoing cooperation with Italian researchers, Professor Cristini Artini, Professor Riccardo Carlini, Professor Roberto Spotorno, and of course, I hope I'm, Professor Riccardo Riccardi, and maybe she has retired, but Professor Gilda Zanichi from University Genoa. And we have ongoing discussion for cooperation with Italian researchers like Professor Dario Narducci and Professor Carlo Fanciulli and other professors. So, so these are things which are going on. And there's a lot of things written here, but my talk will be very conceptual, not so complex. And first I'd like to introduce this thermoelectric. So what is it? It's basically a way to use solid state device to convert waste heat to electricity. And it's based on Seebeck effect discovered around 200 years ago. So basically when you apply a temperature difference like heat, for example, to one side of your material, the electrical carriers will diffuse to the colder side. And this basically when there was no temperature difference, it was balanced, but this is creating the voltage. So this is a sort of basic idea of that when you apply the heat, you can create a voltage. So this is a Seebeck effect. And the good thing for us is this is proportional to the temperature difference. So larger temperature difference, you get a larger voltage, just linear, and this is a Seebeck coefficient. So there are many ways you can imagine to use like convert heat to electricity, because we have a lot of waste heat all around us. So primary energy that we consume, this is a fossil fuel. This is a huge amount of energy, as you can see. So all gas, oil, coal, and so on. And actually, we only effectively use 1/3, and 2/3 is lost. And much of the loss is in the form of waste heat. So this is a huge amount of energy, which is just like thrown away. So what we'd like to do, of course, is to try to partly convert using these thermoelectric materials into useful electricity. And of course, in the bigger scope, we need a better control of the thermal energy, thermal management to try to reduce the loss in the first place. And there has been like some initiative from the Ministry for Thermal Energy Control. So I happen to be one of the referee for the funding project and how to control the thermal energy to a higher degree. So this is an important topic too. Okay, and probably all of you also can imagine many ways to use change the heat to electricity, which can be useful because we have so many heat sources, like from large, like car, to small, like, I forgot to turn on my watch, but small, like using body heat, for example. Okay. And one aspect, so it was in my title for IoT, like energy harvesting, with the senior friendly community or all sorts of things becoming more AI, that it's estimated we could have like 1 trillion sensors all around us. So this is a huge amount of sensors which will be necessary in the future society. But of course, if you try to use a battery to power these sensors, you have to change the battery at some point, and this is like too much trouble. So the idea, of course, we have some energy harvesting to dynamically create electricity, and so you don't need like to change the battery. So maybe it will be a charged battery, but in any case, you have some dynamic system to gather the energy. And for us, this is a thermal energy, thermoelectric. So it's particularly good for us because the Seebeck effect is linear, as we have seen, and there's no scaling effect. So for small heat, like body heat, you can get a small electricity, which could be enough to power a sensor. So this is sort of the idea. And there are, of course, many devices we are interested in working on now. Okay, now I'd like to go a little to the difficulty of the thermoelectric, because we saw all the attractive things, like so much waste heat, so many possible application, but no wide-scale application in the store for the power generation. For cooling, there are many applications, but not for creating electricity. And one problem, of course, the performance of the conversion is not good enough. So fortunately for us, we have a very good way to measure the performance of the thermoelectric materials called figure of merit, and it's based on very fundamental, like simple physical properties. So no like complex application, but just really fundamental science. You can get this ZT. So one benchmark is usually like more than one is considered to be a good performance thermoelectric material. And the ZT is related to the conversion efficiency. So this is the ideal efficiency. If you have ZT like infinity or very large, it will approach this kernel, the ideal efficiency. So of course, we want to get the ZT as large as possible. But one problem is we have physical property trade-off. So it can be seen here. We want, of course, large Seebeck coefficient, like an insulator, but large electrical conductivity, like metal. So right here, we already have some problem. And another problem, we want a material conducting electricity very well, but blocking the heat. So intuitively, this is, of course, to keep the temperature difference. So let the electricity through, but blocking the heat. So this is also a little paradox that we have to overcome. So how do we do this? So this is a very interesting, like fundamental material science. So the last part, the later part on blocking just the heat, if we look at the thermal conductivity, it's made of two parts. So one part is by the electrical carriers, but we need the electrical carriers, so can't do much about this. But the other part is the thermal conductivity carried by the material lattice part, so phonon. So if we can lower the lattice thermal conductivity a lot, then we can just increase the ZT, or the figure of merit. And one very powerful way to do, which is known, is a nanostructuring. And the key of the nanostructuring is basically it utilizes the fact that the electrical carriers and the phonons which carry the thermal energy will have different length scale. So basically, for thermoelectric material, usually this is small, And if you can make like nanostructure or nano microstructure in your material, like the phonon mean-free path, this will be very effectively scattered. And the electrical part may have a small penalty, but still the phonon will be blocked more, the heat will be blocked more. So this is a sort of basic idea, not made by us, of course. I think the first people probably are the American professors in the MIT probably who proposed this idea. And now the idea is how to make a proper nanostructure. So there are many different ways to make, which we also have explored. But one very nice way by a former postdoctor, Atta, a very nice result, is we worked on this scuterdite. So you may be familiar with this material. It's an antimonide, antimon cage, and has this rare earth, very heavy atoms which are not so strongly bound in these voids and have some sort of, can have some movement. So maybe the understanding of this is changing now, but one understanding is this: in the old time, this was an Einstein oscillator scattering the acoustic phonon. So you had some mechanism scattering, but the rare earth is not so attractive because it's like strategically, it's very localized in the world. So this is not so good. And so we want to do rare earth free. But if you don't have this atom blocking the heat, you have like not so high performance. So we try to get it with different kind of nanostructuring. So of course the time is limited, so I go a little quick. But basically we had a very simple way to create a nanostructure, just precipitate this secondary phase, low melting point, and just anneal. So it's very simple. Just you have to only anneal it and it creates these pores. So these are micropore, probably these one here, but the majority of the pores are nanopore. And this had a very strong effect to scatter the phonon and result in a very large reduction of the thermal conductivity. The electrical part, only a small damage. So overall, like 100% enhancement with no rare earth. So this was a very good result by Atta. And a recent result by a very recently departed postdoctor, Jing. She worked on this germanium telluride material, found a unique like chromium doping effect where the chromium dope lowered the vacancy formation energy and created like many vacancy, but many precipitation in the material, which were also very effective to selectively scatter the phonon and lead to this ZT2. So some nice result like in the phonon scattering, selective scattering, the nanostructuring part. Now the other part. So what was this about, like insulating Zwick large like an insulator, but electrical conductivity large like a metal. So the problem we have here. And there are different ways. So one way is a nanocomposite. Again, a former postdoctor, Amir, put these nanoparticle of oxide in this bismuth telluride material to achieve very high performance, like 1.5. And this idea is basically when you have these interface of different material, you can have an energy barrier and only the high energy carriers go through. And the Zwick is basically the entropy per electrical carrier. So you have it can boost up the Zwick. So this was the idea, not by us, again, by American professor. Of course, it's very important to effectively implement these principles, and we get this high ZT. So this was another nice result by this enhancing the Zwick, boosting the Zwick. And now the main part, so this was, I should say this was originated by us, mainly by my colleague Tsuji-san, initiated this work on the magnetic semiconductor. So the idea, of course, so it came a little first finding a good example, but of course the background of this is that magnetic semiconductor can have a very strong interaction between the carrier and the magnetic moment. So this can lead to a heavier effective mass for the electrical carrier, which lead to a large Zwick coefficient. Of course, it can lead to lower mobility, but the Zwick coefficient is most important. It's a square in the power factor. So with this, we thought we can enhance power factor, like enhance the combination of the Zwick and electrical conductivity. And the initial work was found by these rocks of chalcopyrite that a little carrier tuning, we get a quite respectable result. So I'm sorry that I forgot to start my watch. So not sure time, so I'll just wrap it up, but just mention some nice contribution like underwater volcano rocks creating out of electricity. So this is 100% natural thermoelectric generation on the ocean floor. No like man touched it. Something interesting. And of course, the magnetic effect was very clearly proved here that that in the non-magnetic material, introducing this magnetic material, you get this magnetic interactions pretty strong. And actually proportional to that, you see the electrical carriers becoming heavier. And overall, we get enhancement of the power factor. And this is also shown here by some former, this is a professor from UK, with no carrier change, just a pure magnetic effect. Indeed, if you have strong coupling, you get an enhancement. And another nice, very nice work, Tsuji-san found the spin fluctuation enhancement effect for the Xebec. This is in Science Advance. And basically, this was proved by applying a magnetic field and suppressing the spin fluctuation, which shrinks the Xebec, and shown here. And actually, this effect, it looks to be small here, but we only apply like a small finite magnetic field, and the enhancement effect can be what we've estimated, like 50% of Xebec enhancement by spin fluctuation, quite large. And a collaborator in Europe, in Vienna, made these materials a thin-film form, and actually there appeared to be modification of density of state, leading to a very high ZT, very high power factor published in the Nature. So these are some like interesting development found, especially in this magnetic semiconductor. So I won't go in this part, but just show we're interested in many different inorganic material, and just finally wrap up. So thank you for your attention, and we're very interested in collaboration, particularly with our Italian research friends. So thank you for your kind attention.
Thank you very much, Takao, for this very interesting talk. Now we move to our last talk in a scientific session. It will be, last but not least, Anna Maria Petrozza. Anna Maria studied at Politecnico di Milano and in Paris. And then she got her PhD in physics from the University of Cambridge. And now she's a senior researcher at the Italian Institute of Technology, leading the Advanced Materials for Optoelectronic Group. Thank you very much. So the floor is yours, Anna Maria.
Can you hear me? And
yes.
Hello. Okay, I'm sharing my screen. Is it working? Yes. Okay. Thank you. Perfect. Thank you. Thank you very much for your kind invitation. I believe it's a great opportunity, and I've been actually also in the past working with the Japanese company. So I've been working for Sharp for a few years while developing dye-sensitized solar cells. So today I'm going to introduce our activities on perovskite, on metal halide perovskite semiconductors, especially for solar cell, but in general for optoelectronic application. So we have been hearing about the perovskite also in the previous talks. Metal halide perovskite are actually, and is actually an ionic solid, which can self-assemble close to room temperature. Thus, the crystal is mainly built on ionic and sometimes hydrogen bonds. The structure, the general chemical formula of this type of perovskite, which work as a semiconductor at this time, is AMX, where X is generally an halide anion. M is a metal cation, which can be lead or tin, and A is an inorganic or organic cation. So the first two makes the inorganic cage through this sort of octahedra, while the A cation is generally in the middle of this cage. So the first two mainly form the main bonding orbitals. So in a first approximation, they determine the electronic band gap of the semiconductor, which can be tuned, changing the chemical composition. What you can see here on the bottom is a thin film made of perovskite with different band gap, while the cation in the middle is mainly there for structural tuning. As you can see here, you can change the nature of the cation, you can change the size, the functional group, and change these. You can play with actually, you can change the structure of the metal halide perovskite, for example, moving from 3D to quasi 2D, 2D, and going to actually 0D semiconductor. You can also simply control the way the inorganic part is growing. And since they are responsible for the electronic property, you can actually manipulate the electronic property of the semiconductor by manipulating the structure of the crystals. So we are in front of a pretty large library of materials with different type of functionalities that you can actually apply also for different application: quantum optoelectronics, lasing, LED, and of course photovoltaics, which has been actually the first application where these materials flourished. Now, what is the curious property characteristic of these materials? They are mainly solution process materials. They are ionic solids, and they are characterized by there are different evidence of disorder, presence of defects, traps, which you would expect from a material that is synthesized close to room temperature, that is prone to a large, in principle, to a large density of different type of defectivity. We have evidence of static disorder within the unit crystals. We have evidence of dynamic disorders, ion motion because they are ionic, and trap-mediated emission dynamics. What you can see are on the bottom right, for example, is the normalized PL quantum photoluminescence quantum yield as a function of the excitation density. And you can see that you need to fill all the trap before getting to the band-to-band emission that you would expect for a very good semiconductor. Nevertheless, this material, since the beginning, since the first application in a solar cell, they show very little losses, so very impressive primary optoelectronic properties. Direct band gap, very long diffusion length of carriers, very good light absorption. And here on the left, I'm showing the VOC of solar cell as a function of the optical band gap. So this is a way to really roughly evaluate the importance of losses in solar cell. And you can see that in perovskite, since the beginning, this loss was very minimal. And today, we are able to fabricate champion photovoltaic cells with a power conversion efficiencies, which is of the order of 25%. This means that is close to what silicon solar cells are showing in the lab. Now, but these materials can be synthesized and processed at very low cost with very simple methodologies, which is prone to scale up. Now, what we have been doing in the last few years in our group, we have been mainly trying to understand from why with this material we can talk about defect tolerance. So why we have evidence of the presence of defect, but they seem to not affect the performances of the materials, and why and how these materials react to external stimuli. because on the other side, what has been the main what has raised a sort of skepticism in the community regarding the real transfer of this technology from the lab to the market has been the stability of the material. As you can understand, if we can make a material close to room temperature, we can also destroy the material close to room temperature. So I would like to start our investigation from some theoretical prediction. These are data from a colleague of mine, the group of Filippo De Angelis in Perugia. So when you want to understand the role of, which type of defect we have in a material and how important they can be on the performance of the semiconductor. The first thing you need to know is the defect formation energy. What we can see, the first thing, and the other important thing is the thermodynamic ionization levels of defect. This means if you have a high density of defect, where these defects actually introducing a trap, carrier trap state within the band gap of the semiconductor. In this case, they would be detrimental. Otherwise, they may not affect the property of the semiconductor. So what we know from these studies is that the large density of defect belong to vacancies, mainly of the cation, that is the organic cation, which is in the middle of your cage, which generally is a methylammonium cesium cation. But there is a density which is low but is not zero of allied interstitial, which actually introduce, as I'm showing here, defect trap state within the band gap. What is the characteristic of these states? These allied interstitial are able to have an amphoteric character. What does it mean? So they can trap both electrons and holes. But what happened here, I'm showing on the left, the red curve, when they trap where they can trap an electron, they need to overcome an energy barrier to trap this electron. At molecular level, the defect needs to rearrange itself once the electron is trapped, and we have a kind of a neutral state, which is this I0 species that I'm showing here, which is metastable. And to release the electron back, so for the electron to recombine with holes, so we need to overcome another energy barrier. So this means that we have a thermally activated electron trapping and a very long lifetime of electron. On the other side, the trapping of holes and the trapping, so recombination of holes, is very fast because it doesn't see any energy barrier. So this is what theory is predicting. What we observe from experimental point of view. Here I'm showing an example with a methylammonium lead bromide. And what we could find is actually the existence of two sub-band gap states. You can see the emission here on the left. So one in the blue, one of the red, closer to the optical edge of the semiconductor. And the one more in the near infrared has an extremely long lifetime of the order of tens of microseconds, while the one closer to the optical edge, which is responsible for trapping holes, what we experimentally prove, has on the other side a very short lifetime. So to recap, what we know about these materials is that they have intra-gap carrier trap state that can be have been experimentally proved. They are related to the allied interstitial point defect, and they have a peculiar characteristic. They can trap also with a very fast trapping and recombination time, or they can trap electron with a very slow trapping and recombination time. Of course, this happens. This these states all belong to a light interstitial, but to a light interstitial with a different oxidation number. So they are not, of course, exactly the same thing. Now, why this can explain the defect tolerance of perovskite? The first thing we've been doing has been looking at the photoluminescence quantum yield, which is a sort of is a good figure of merit to evaluate the quality of your semiconductor. So you excite with photons, we see how many photons are getting out. The dot line here is the photoluminescence quantum yield if we consider only the trapping rate of carriers. The red lines belong to a situation where we have an excess of a whole trapping state, the very fast, with the one with the very fast dynamics. The black one are a situation where we have an abundance of electron trapping states. So the trap carrier which have a very long lifetime. So as you can see, especially a low excitation density, which are relevant for photovoltaic application, and they are comparable to the density of defects you can find in perovskite, in three-dimensional perovskite. When in the case we have an abundance of electron trapping state, the long lifetime of trap carrier reduces the effective density of trap state. In fact, once you trap an electron, this lives so long that is somehow self-healing that defect. So if another photon comes, finds that state already occupied, so it doesn't get the electron doesn't get trapped again. This is a sort of self-healing of the material itself. How this becomes important when you look at the open circuit voltage of a photovoltaic device. So if we imagine that the open circuit voltage in ideal case is simply due to the splitting of the quasi-Fermi level of the semiconductor, we consider a band gap of 1.65. In presence of a pure band-to-band recombination, we expect an open circuit voltage of 1.3 volt. Now, if we simulate a situation where we trap and recombine charges very quickly, so we lose charges actually, the open circuit voltage has an important loss and it goes to 1.14. On the other side, if we have long-lived carrier trapped, so long-lived free holes in this case, the loss becomes much smaller. So this can explain why, despite the fact in this material we have a high density of defect, they either introduce shallow traps, as in the case of vacancies, or they have this peculiar chemistry which makes the trap carriers less detrimental. Now, what is very important, this is a kind of empirical observation I'm reporting. On the left, you see how the power conversion efficiency has improved with improving the open circuit voltage of the solar cell. And what I've been finding is that during the last 10 years, while at the beginning we were observing mainly spectroscopic features related to all trapping states, the detrimental one, over time, we observe mainly defect states related to electron trapping states, the good one. And this happened somehow through a modification of the processing of the material. So during time, what happened, what we have been doing a bit of empirical way, has been changing the process of the material, unbalancing the density of electron trapping states with respect to the other one. And this can mainly happen when we change, for example, the oxidation environment of the processing of our thin film. A mild oxidation environment can actually exchange or change the oxidation number of your defect states. So this is a kind of demonstration how a better control, knowing, I mean, what is the photochemistry of our system, we can lead to a better control of the processing and improving our device. So now that we know which type of defect we have, how we can understand also the material reactivity to stimuli based on such defects and the stability of the material. For example, when we expose a perovskite, metal halide perovskite to oxygen, we have been observing an improvement of the emission properties, so of the photoluminescence efficiency. And we know, knowing the spectroscopic feature of defect, that is mainly due to a passivation of halide interstitial, which induce the main loss in the semiconductor. So oxygen is mainly passivating this defect. And how this happen? This happen mainly reducing this halide interstitial, forming a product which will move the deep defect states to shallow defect states, so closer to the valence band, or actually transforming the halides, the hole trapping halides effect in an electron trapping halide effect, which in this case is a 3-iodide. Now, what happened under light? What we found is that when we excite metal halide semiconductor, so under light, we are actually inducing the formation of defect. So you see here the relative PL quantum yield when we increase the excitation density, and then when we go back, and you see there is a sort of hysteresis, which is mainly due to the formation of defect states. And as you can see here, we are definitely forming, increasing the density of a hole trapping states. So this was a sort of a dilemma in our group, and also in the, as I can say, in the field, because there were two very different observations by different groups. Few of us were observing a photo-induced defect healing. Under illumination, the performances of the emission, for example, was improving. Some of us were observing photo-induced degradation. And you can understand that this is an important point if you want to use this material as a photovoltaic system, when you need to irradiate it for many hours. What we found, kind of solving this dilemma, is that the two phenomena are actually coexisting. So you can actually observe both quenching and healing of defect, changing the experimental condition. So on the left, for example, I'm showing the integration of photoluminescence over second when we change the time of between illumination and dark for your sample. So the repetition rate in this case of our laser. And what you see is that closer to CW condition, you observe a quenching. When you reduce the illumination time, you start observing an healing phenomena. And same thing happen when you change the temperature of your system, which means that you are providing extra energy to your to the semiconductor. What is interesting, what we found is that actually if we stay at room temperature and we are in a CW condition, which is the working condition of solar cell, we can switch off the photo quenching phonomena, which happen in the pristine perovskite thin film, which is the dark line on the left, to only a photo healing phenomena when we use a proper passivation of the surface. We passivate the perovskite with a polyethylene oxide layer, which is, has a technological relevance. Is also good for the fabrication, easy to use in the fabrication of solar cell. And you can see on the right, we also fabricate a solar cell. This one was a few years ago on about 20% power conversion efficiency. And you can see that the passivation, the passivation of the perovskite surface not only improve the VOC of the solar cells, but also stabilize over time the open circuit voltage, as we can see in the photoluminescence. So photoinduced formation of trap states and trap healing phenomena coexist and compete, and effective surface passivation can switch off the trap formation. What is happening? And here I'm close to finish my presentation. What is actually happening? The polyethylene oxide is passivating, is forming lead oxide bonds on the surface. So it's passivating the undercoordinated lead on the surface. Nothing directly in the first passivation, nothing to do with allied defect. Nevertheless, this is the landscape. So this is the explanation we have. When we trap an electron or holes, what we do is we actually reduce the activation energy for a Frankel defect, where you see interstitial and a vacancy close to each other, to collapse onto each other. This means that we are left with a reduced density of defect, and this can make us observing the healing phenomena. And this I0 species, which is this metastable species, which will have the lifetime of the trap carrier. So in a situation where we have a low density of defect or low illumination density, this I0 will then go back and will release the carrier. But if we have a high density of I0, which means close to the surface, for example, where we have a high density of defect, or under high illumination intensity, I0 can go through a bimolecular process and form I2. I2 doesn't like to be in the bulk and will travel towards the surface, where it will get stuck on site due to the undercoordinated lead. And in this situation, the I2 can get out and will trigger a catastrophic reaction, which will form more and more defect in the bulk. If we passivate the surface in the proper way and we heal the surface defect, I2 won't be able to escape, and we go back, and we will be left only with the photo healing mechanism. And we prove it experimentally, trying to probe the I2 release in solvent when we illuminate the thin film of perovskite, and we can see that actually when we passivate it, the I2 is strongly reduced. Now, to conclude, what's next? What we are trying to understand is which are the optimal charge extracting layer in solar cell, which can prevent the release of I2. And we are trying to understand more how the density of native defect is related to the nature of the chemical composition and the structural characteristic of the perovskite. And here I close, thanking the team, my team here in Milan, and the funding agency which allowed us to work. And I thank you for your attention.
Thank you very much, Anna Maria, for this very interesting and comprehensive talk. So now we are ready for question and answer. So I have first a question from, I will give the floor to Gianni Grasso, who has an answer for Professor Murakami.
Yes, thank you very much. I have a question for Murakami-san.
Yeah.
I would like to have your opinion on, on the possible impact of the hydrogen economy on superconductivity. You know, of course, very well that Japan is probably at the lead on the hydrogen economy, and also liquid hydrogen, right? And we know that liquid hydrogen may be really an ideal way to refrigerate many HTS superconductors. So how do you see this as a possible push for our, superconducting technology? And do you already have R&D programs in Japan on this topic, or you are expecting to have programs that may, merge HTS and hydrogen in a common product? Thank you.
Well, thank you, Jansen, for your question. Yes, if people start to use liquid hydrogen as fuel, I think it's a good chance for high temperature superconductor to widespread because the temperature of liquid hydrogen in 20K and low enough for the application of high temperature superconductors. And in fact, about 20 years ago, I worked with the team from NASA, that's the Japanese NASA, to make a liquid hydrogen pump, but mainly for space applications. And I also levitated the liquid hydrogen cylinder. And there was an idea to install superconducting transmission cables in liquid hydrogen pipeline because, if you want to make a pipeline, you don't need to cool the superconductor, already liquid hydrogen is there. So it's going to be really interesting area for superconductors if people start to use liquid hydrogen. Yes, I believe we can have a lot of devices based on liquid hydrogen applications. Thank you very much.
So
is it okay?
Is the answer is okay?
Yeah, sure. Thank you very much. Thank you.
Okay. Mm-hmm.
So now I have a question both for Takao and Anna Maria by Dario Narducci. Dario,
yes.
The floor is
yes.
yours.
Yeah, thank you. First of all, thank you very much for this very nice workshop and for the old presentations. I have a general question concerning the possibility of coupling different sources of different ways to generate electric power together. I'm referring to the possibility of coupling photovoltaics with the thermoelectrics. Maybe some of you know that I've done some work in this direction. The main issue normally is that when you have to pair these two type of objects, you go in a problem because they work well in the opposite conditions. Photovoltaic cells like to be cold, while thermoelectrics need high temperature. Now, with many years ago, Professor Komoto there in Japan thought about the possibility of doing this sort of coupling using very sensitized solar cells, which were unfortunately very unstable at the time. Perovskites open a new possibility. So my request for you is a comment on how you see the opportunity to you reuse the heat released by photovoltaic cells based on perovskites to add an additional stage of conversion through thermoelectricity.
So I think that I will ask first Takao to reply and then Anna Maria.
Okay, thank you, Dario, for a very nice question. And I agree. I think there's good possibility to have this like both conversion technologies, especially I think probably as you pointed out that photovoltaic uses a particular wavelength, and actually the heat generating part is not used, so thermoelectric could be an assistant to that. And as you pointed out, there were like 2004, I think there were some project for the cogeneration project, but from that time, the technology of thermoelectric and the development of materials for both PV and thermoelectrics came quite a way. So I think you have a very good point that this should be like reinvestigated again with like up-to-date new materials. And especially high temperature, I think this is viable. And now with this push for the room temperature, near room temperature, like wearable or so on, there could be a very good combination for the like our wearable near room temperature like body heat and photovoltaic generation combination. I think it's a good point, and hopefully we can explore it. So thank you.
Thank you, Kekal.
Okay, on my side, I should say that honestly, I don't have the numbers in mind, so I don't know exactly for especially for photovoltaics. What actually I think is another opportunity for coupling in terms of perovskite is the lasing application of perovskite. Because this metal halide perovskite can be extremely promising for electrically pumped laser. And in this case, we really need to get rid of heat, and it's probably higher than the heat you can have for photovoltaic devices. Yeah, so these may be possible. I mean, some possibility in terms of coupling. Regarding photovoltaic itself, as I repeat, I don't have the sensitivity of numbers, so I don't feel like I can really comment on that. We are also trying to work, I mean, this can be an interest I mean, to see if this metal halide perovskite can be used also as thermoelectric materials. At the moment, they are intrinsic semiconductors, so no way. But it's interesting to we are trying to investigate and see if there are opportunity for electronic doping, because in terms of thermal conductivity is ideal. We need to have also carrier going through.
Okay, thank you.
Thank you very much to both. And now I have a question for Elisabetta. Elisabetta, your anode is rather interesting, and the performance in methane is really promising. But you use this with LSGM electrolyte. I wonder that probably the impact would be much larger if you were using it with Syria, for instance, or for other electrolytes. Did you make any measurements with different electrolytes than lanthanum gallate?
Can you hear me?
Yes.
Okay, thank you, Enrico. Yes, we used our anodes both in LSGM electrolyte and GDC-based fuel cells. The measurement with the GDC electrolyte supported cells were, I mean, the polarization resistance we found were much lower than we found with the LSGM. But the problem is a well-known problem on the stability of GDC for a long time, especially in reducing conditions. I think that GDC, as now it's almost consolidated, that cannot be used as electrolyte. It is better, I mean, with LSGM, the performance were good and the stability also. With GDC, we observe yes, a degradation, which is due to the electrolyte itself. What I think maybe for a practical application, still YZ is maybe the best electrolyte for commercial application, reducing the thickness and using GDC as a buffer layer at the interface, more than LSGM maybe, because when we think to use hydrocarbons, we cannot think to reduce that much the temperature, otherwise the methane oxidation or reforming cannot take place. So we always use LSGM by our side because it's our common internal reference in our lab, which is of course a good electrolyte conductors in the intermediate temperature range. But maybe what I think for practical application, still YZ sufficiently thin with eventually with GDC as buffer layer is still the best performing electrolyte for FSOFC.
Thank you very much.
I don't know
Elizabeth.
if you
Yeah,
do
yeah,
agree
it's
with
very
this.
clear.
Okay, thank you very
Clear.
much.
Thank you. So there is a comment on Miao Lei general on the observation of the discussion between Dario and Takao and Anna Maria. I don't know if you want to make a general comment.
Yes, thank you for chairman. So I'm Lei Miao. I have some experience, research experience on the heavy type of PE module with combined with photovoltaic. But I think the problem is the low efficiency of thermoelectric module and also material. So even if we change to photovoltaic, perovskite type solar cell, so I think we should solve the problem for increasing the efficiency for TE module. Yeah, still searching for high ZT value, good thermoelectric conversion material. Yeah, that's my opinion. Thank you very much. Yeah.
Anyone who wants to add something?
Yeah. So thank you, if I may be allowed.
Sure.
Thank you for this comment. It's true, of course, near the room temperature and small delta T, the efficiency thermoelectric is very low. So, but I think for the applicative purposes that we need to get like as much power generation as possible. And so I think for the near room temperature like application, this is a matter like not like solving a problem like taking away heat from the photovoltaic, because of course this is like very low efficiency, this is not effective. But the main issue is probably like the combined technology can generate more microwatt and you can have more energy to power your electrical energy to power your sensor. So I think there can be a combined effort, like using body heat and like the like sun, like rays of the sun, and you could hopefully get like more power generation from these two technology to like power what device you need. So I agree. This is a good comment. That indeed, the thermoelectric is not so useful like to try to like remove the heat, like take away the heat. This is like only very high ZT material at very high temperature, large temperature difference, it starts to get some good efficiency. But in general, it's not really meant as a way to like remove unwanted heat, but producing useful electricity. So that's, I guess, main focus, and combination would be good, because I think just thermoelectric, maybe we don't have enough electricity. Just photovoltaic, maybe that's not enough to power many devices. So I think the combination could be viable. So just a comment.
Yeah. Yes, I think gather heating from the body is a good idea, but how to design the heat source and cooling source, and also also the heat from the PV side, how to use it. Yeah, we should solve that problem and then make it working well.
Thank you very much.
Yeah.
So we have a last question from Alok Jha for Professor Murakami.
Can you hear me?
Yes.
Thank you very much, Professor Murakami, for such an inspiring talk on superconductivity. So we all know that the twin boundaries are considered as a planar structures, nanostructures inside the Rebco films. So I always wonder about the efficiency of these as our pinning centers. What temperature or applied magnetic field range these structures are effective as pinning centers?
Well, twin boundaries.
Yeah.
I think it depends on the direction or how fluxoids are distributed in the superconductor.
Yeah.
And twin planes can act pinning centers only when fluxoid try to cross the twin boundary.
Oh, yes.
If they move along the twin boundary, they cannot act as pinning centers. But if you have the structure with various grains where the direction of twin boundaries are different from grains to grains,
yeah,
they can act as, because there is a direction for the twin boundaries can act as pinning centers.
Yeah.
So in the total pinning forces, you can calculate how effective they are. So, but depends on the direction and the distributions.
Yes.
And if you have, you know, like a synchrostal, where the twin planes just align in the same direction, in this case, they can act as pinning centers only when Lorentz force on fluxoid acts perpendicular to the twin planes.
Yeah, right.
Yeah, so it depends on the situation. But if you have very small grains, where there are lots of twin planes have directions in various directions, then they can act as somehow pinning centers effectively.
That's a good point, but that is limited actually to the geometrical dimensions of the flux lines.
Yes.
So I'm curious to know about, like, what temperature or magnetic field range could be considered as
well, right now I have no data, but of course there is a temperature range and also field range where the twin boundaries can act as effective pinning centers.
Okay.
Of course, it depends on the temperature range and the field range.
Thank you.
You're right. Yeah. Okay.
Thank you very much. I think we have ended the question and answer session. Paolo, do you want to say something, or are you closing?
Yes. So I want to thank all the speakers and for the very interesting talks, and also attendance for nice questions. And I have a comment. Maybe it's trivial, but I was believe has been much more easy to to host a virtual conference. So I feel something strange. So of course the conference was very good, but I think we are not still accustomed to this kind of interaction behind the screen. So we need a human touch. So I hope we will come back to the normal life soon, and to have a real conference and real gathering also is very important. So this is my hope, and I think it's a hope of all of you. Okay, so thank you again. And we have a record of this talk, so we will discuss how to share. And I want to pass the microphone again to Enrico for final remarks. Okay, thank you.
Thank you very much, Paolo. So as a general remark, I think it's the common thread of the talks was the investigation of materials, how to process, modify the macrostructure of materials for improving the performance. It's a bit trivial observation, but it's always nice to point out the importance of materials for many applications, including renewable energy, and so fight to climate change. I'm thinking, I want to thank for the speakers for the very interesting talks and for accepting our invitation, and the Shibaura Institute of Technology, Professor Murakami and Paolo Mele for organizing everything. I think it's, in this kind of situation, it's refreshing to hear a little bit about science instead of virus, because the talks, it's always about virus recently. So it's nice to hear finally again some science. And so let's put it as a starting point. And if we were together, this would be the moment for a campai and maybe for some Italian food, some toast. This is not the case. Just I make a virtual toast and so campai for everybody.
Kampai.
Okay.
Thank you again.
Thank you.
Thank you.
Thanks again.
Thank you.
We can close the workshop here.
Okay.
Thank you very much.
Thank
Okay.
you. Bye-bye.
Thanks. Bye.
Bye-bye.
Bye-bye.
Thanks. Bye.
Bye.